everything you thought you know about black holes could be wrong. The theory from one of the most brilliant scientists of the 20th century, Albert Einstein, might be proven incorrect thanks to the work of a genius New Zealand mathematician named Roy Kerr. Kerr, who first described black holes mathematically in 1963, has demonstrated that the singularity at the center of a black hole, the point where all of its mass and gravity is concentrated, does not actually exist. This contradicts the conventional understanding of black holes that Einstein and others had accepted. According to the long-standing view based on Einstein's theory of general relativity, the immense gravitational force of a black hole causes the fabric of spacetime to become infinitely curved or singularized at a single point at the center, known as the singularity. The singularity contains all of the black hole's mass with effectively zero volume, resulting in infinite gravitational forces. Around this singularity lies the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. The intense gravity of the singularity is thought to suck everything past the event horizon into itself, obliterating anything that crosses that threshold. This view depicts the singularity as the actual black hole itself, with the event horizon simply being a consequence of the singularity's extreme gravitation. If there is no singularity, then the existence of black holes themselves could be called into question. Indeed, the first image captured of a black hole by the Event Horizon Telescope in 2019 appeared to show the hallmark lopsided ring of the accretion disk surrounding a black hole and its event horizon. So if singularities don't exist, what exactly is at the core? This is where Kerr's groundbreaking work offers a potential resolution to a paradox that has plagued black hole theory for decades. Kerr's mathematical models revealed a critical flaw in the assumption that black holes are stationary, non-rotating bodies required for singularities to form. Due to the law of conservation of angular momentum, any collapsing star that forms a black hole should maintain its initial rotation unless impacted by an external force. If the black hole itself is rotating, then Kerr demonstrated that the matter falling beyond the event horizon would not converge on a single point as depicted in conventional singularity models. Instead, the material would orbit around in a ring-like motion rather than collapsing inward. In a rotating black hole model, the immense gravitational forces do not concentrate all of the mass at a single central point. Rather, the matter distributes around the black hole's rotation in a ring-shaped singularity, avoiding the existence of an infinitely dense singularity. So while immensely powerful gravitational forces still exist within the event horizon of a rotating black hole, the singularity avoids the paradoxical scenario of matter being crushed into an infinitesimal singularity point with infinite density. The singularity represents a departure from Einstein's conception of a single infinitely dense point, but one that resolves some of the contradictions and violations of physics resulting from singularities. If Kerr's singularity model proves accurate, it could have profound implications for our understanding of black holes, gravity, and physics in general. However, Kerr's work doesn't completely invalidate Einstein's theory of general relativity. While it contradicts the specific notion of singularities, much of modern physics and technologies like GPS still rely on the principles of general relativity that have been repeatedly validated. Kerr's model could be viewed as refining and expanding the applicability of general relativity rather than discarding it entirely. Just as Einstein's insights built upon and offered a new perspective on Newton's theories of gravity, Kerr's work could represent another evolutionary step in our understanding of this fundamental force. With a singularity rather than an infinitely dense singularity at their cores, scientists may need to re-examine phenomena like gravitational lensing and advance new theoretical models that better align with empirical observations of black holes. As Kerr himself reflected, "I can't help but quote the philosopher, there are more things in heaven and earth than are dreamed of in our philosophies." The singularity of black holes may not be what we dreamed after all. Rather than pushing inexorably toward a final theory of everything, science often advances in a recurring cycle of creation, validation and revision of models as new evidence and insights emerge. Whether the singularity theory withstands further scrutiny or cedes an even more evolved understanding remains to be seen.